In this video, we will talk about how to perform the sensitivity analysis and how to explain the shadow price for linear programming problems. In this video, sensitivity analysis is used to answer two types of questions. The first one is, how do the changes in the available resources affect the optimal solution? The available resources are represented by the right-hand side in the constraints. The second one is, how do the changes in the unit profit or unit cost affect the optimal solution? The unit profit or unit cost are represented by the coefficients in the objective function. Here is an example. Two machines are used to produce two types of products. A unit of product 1 requires 2 hours of processing time on machine 1 and 1 hour of processing time on machine 2. A unit of product 2 requires 1 hour of processing time on machine 1 and 2 hours of processing time on machine 2. Daily processing time available on each machine is 8 hours. Selling 1 unit of product 1 will generate $300 net profit. Selling 1 unit of product 2 will generate $200 net profit. Now we let x1 be the number of product 1 produced, and x2 the number of product 2 produced. We can formulate a linear programming problem to maximize the daily profit, which is the total profit of selling products 1 and 2. The first constraint means that the total processing time on machine 1 should not exceed 8 hours. The second constraint means the total processing time on machine 2 should not exceed 8 hours. This problem has only two variables. We can solve it graphically. This is the constraint of machine 1 and this is the constraint of machine 2. This shaded area is the feasible region. This point A is the optimal solution. The objective function value at this point is 4,000 over 3. Now let's perform sensitivity analysis on the right-hand side of the constraints. For machine 1, we want to know if we change the available time by 1 hour from 8 to 9, how much will the z-value change? In this graph, the constraint for machine 1 will be changed to m1 prime, and the optimal solution will be changed to point B. The objective function value at this point is 4,400 over 3. The shadow price of machine 1 is defined as follows. The new z-value minus the old z-value divided by machine 1's capacity change. So the shadow price of machine 1 is $133 per hour. It means each hour increase on machine 1 will bring in 133 more profit. For machine 2, we can do the same. We want to know if we change the available time by 1 hour from 8 to 9, how much will the z-value change? In this graph, the constraint for machine 2 will be changed to m2 prime, and the optimal solution will be changed to point C. The objective function value at this point is 4,100 over 3. The shadow price of machine 2 is the new z-value minus the old z-value divided by machine 2's capacity change. So the shadow price of machine 2 is $33 per hour. It means each hour increase on machine 2 will bring in $33 more profit. Now we have the shadow prices of these two machines. Based on these shadow prices, let's answer these questions. First question, if we can increase the capacity of both machines, which machine should receive priority? The answer is machine 1, because if we increase both machines' processing time by 1 hour, the increased profit from machine 1 is much higher than the increased profit from machine 2. Second question, should we increase the availability of machine 1 at an extra cost of $50 per hour? The answer is yes, because $133 is greater than $50. We will still make more money by increasing the availability of machine 1. What about machine 2? The answer is no, because $33 is less than $50. We will lose money and it's not worth it. Now let's perform sensitivity analysis on the objective coefficients. For general maximization problem, z is equal to c1 x1 plus c2 x2. The slope of the objective function is minus c1 over c2. This slope should be between the slope of these two constraints, so that the optimal solution will be unchanged. That means the optimality range of c1 over c2 is between 1 over 2 and 2. With that in mind, let's answer this question. Suppose that the unit profit for product 1 is changed to $350, and the unit profit for product 2 is changed to $250. Will the current optimal solution remain the same? To answer this question, let's check the value of C1 over C2, which is 350 over 250, or 7 over 5. It's still between 1 over 2 and 2. So the answer to this question is yes. Another question. Suppose that the unit profit of product 2 is fixed at its current value. C2 is equal to $200. What is the range of the unit profit for product 1, C1, that will keep the optimal solution unchanged? Now C1 over C2 is C1 over 200, which should be between 1 over 2 and 2. Finally, we have that C1 is between 100 and 400. If it's in this range, the optimal solution will remain the same. Okay, that's how to perform sensitivity analysis for linear programming problems and how to use the results to make managerial decisions. Thank you for watching.